Okay, welcome back. So imagine the AI research world buzzing, right? There's this paper, Shojay et al., 2025, and their big claim that these sophisticated large reasoning models, LRMs, they just hit a wall with complex planning, a real accuracy collapse.
Hmm.
It sounded like, a fundamental limit, like they just couldn't think past a certain point.
Yeah, it definitely made waves.
Yeah.
Sounded pretty definitive.
But maybe not so fast. Today we're doing a deep dive into a really critical commentary by C. Opus and A. Lawson, also from 2025. And they're arguing, well, maybe those failures weren't about the model's thinking at all. Maybe it was much more about how we were testing them.
Exactly. And that's our mission today, really, to unpack how the way you design these experiments can completely change what you think AI can or can't do. By the end of this, you'll hopefully have a much clearer, more nuanced view on this whole debate. It's a really hot topic.
Right. So let's break this down. The original study, Shojay et al., they painted this picture of a collapse. Models just failing on harder puzzles.
Yeah.
But what did Opus and Lawson find was really going on?
Well, this is what's so interesting. Often the models actually knew the right steps. They understood the task. But the evaluation itself, the setup, it kind of tied their hands. It wasn't always a reasoning failure.
Okay, so let's dig into the first big one. Output token limits. Take something like the Tower of Hanoi puzzle. The original tests made the models write out the entire sequence of moves, every single step, exhaustively. And as the puzzle gets bigger, say more disks, the number of moves explodes, right? So the output gets incredibly long.
Exactly. Exponentially long. And the models, they actually seem to know this was an issue. There was this great example cited, I think, from a replication on Twitter, where a model solving a long problem literally said something like, the pattern continues, but to avoid making this too long, I'll stop here.
Wow. So it's basically saying, I know how, but I'm not writing a novel.
Pretty much, and that's a critical difference, isn't it? It's not, I can't figure it out. It's, I'm choosing to stop this super long output because of the constraints.
So the evaluation frameworks just saw incomplete output and marked it as wrong, failing to solve.
That seems to be the issue. They couldn't easily tell the difference between can't solve and chose not to finish this massive printout. And, Opus and Lawson make a really strong statistical point here, too. Even if a model is incredibly accurate, say 99.9% accurate for every single token it generates.
This sounds almost perfect.
Right. But if you need it to generate, say, 10,000 tokens perfectly in a row for one of these exhaustive solutions, the probability of getting every single one right drops dramatically, like less than 0.0005%. It's almost zero.
Okay, so needing character-by-character perfection on a massive scale is just setting it up to fail, statistically, even if the underlying logic is sound.
Precisely. It highlights how this kind of rigid, exhaustive evaluation can really misrepresent what the model actually understands.
And here's where Opus and Lawson really connected the dots, wasn't it? They looked at the actual token limits of the models being tested, like 64,000 tokens for Claude 3.7 Sonnet and DeepSeek R1, maybe 100,000 for O3 Mini.
Yeah.
And they matched that against the formula for how many tokens the Tower of Hanoi solution needs, which grows like quadratically with the number of moves.
Exactly. It's roughly 5 times 2 to the power n minus 1 squared tokens. A lot of tokens as n increases. And what they found was, well, these token budgets physically capped the size of the Tower of Hanoi puzzle the models could even outpound. For those specific models, the limit was around NEM7 or NE3 disks.
So the collapse, the first paper reported,
Happened exactly when the puzzle size demanded more tokens than the model's output buffer could handle. It wasn't a reasoning breakdown, it was hitting a technical output limit.
That's quite something. And they had a counterexample, right, to show the reasoning was still there.
Yes, a very compelling one. They asked the same models to solve Tower of Hanoi for 15 disks way bigger, should be impossible based on the collapse idea. But instead of writing out all the moves, they asked it to generate a simple Lua function that, when run, would print the solution.
Ah, so generating the method to solve it, not the exhaustive solution itself.
Exactly. And guess what? The models did it with very high accuracy, and the code itself was short, under 5,000 tokens.
So freeing them from having to type out the whole thing showed they actually understood the algorithm. They could reason about it abstractly.
That's the key takeaway. It strongly suggests the reasoning capability was intact. It was the reporting requirement that caused the apparent failure.
Okay, so token limits, that's one major issue. But that wasn't all Opus and Lawson found, was it? There was this other thing, the impossible puzzle problem.
Ah, yes. This one's almost, well, it's kind of shocking, really. In the river crossing puzzle experiments, It turns out the original Shojay et al. Study included some puzzle instances with 6 or more actors, using a boat that could only carry 3 people. And it's a well-known result, mathematically proven, that the classic missionaries and cannibals puzzle type, which this is a variant of, it simply has no solution if you have more than 5 people and 5, and the boat capacity is 3, b equals 3. It's mathematically impossible.
Wait, seriously? They were testing the AI on puzzles that literally could not be solved.
Yep, that's what Opus and Lawson uncovered.
So the models were getting 0 scores for essentially recognizing correctly that the puzzle was impossible.
Exactly. It's like, imagine penalizing a specialized math program because it correctly told you an equation has no solution. It's not a failure of the program, it's a correct assessment of the input.
That just highlights the dangers of purely automated black box testing, doesn't it? If you don't deeply understand the problems you're setting.
Absolutely. It shows the hazards of purely programmatic evaluation, as they put it. You might be measuring the wrong thing entirely, or penalizing correctness.
Okay, mine's slightly blown on that one. Let's move to the third big point they raised: how complexity itself was measured. Shojay et al. Used compositional depth, basically, the minimum number of moves, as the main way to say how hard a puzzle was.
Right. And Opus and Lawson argued this is, well, misleading. It mixes up just doing lots of simple steps with actually having to think hard at each step. They use a great comparison. Tower of Hanoi. Tons of moves, like 2N, but each move is dead simple. You barely have to think. Branching factor is 1, no real search needed.
Okay, lots of steps, but easy steps.
Exactly. Now compare that to river crossing. Far fewer moves, maybe around 4N, but each move requires complex checking of constraints. Can't leave missionaries outnumbered, etc. It requires search. The branching factor is higher, maybe 4 or more. It's known to be computationally hard, NP hard, in fact.
So fewer steps, but each step is much harder, involves more complex decision-making.
Precisely. And then you have things like Block's World, which is even harder, computationally PS-space complete, even if the number of moves isn't exponential. The computational complexity of the decision at each step is very different across these puzzles.
So that explains why a model might nail a 200-step Tower of Hanoi solution, but then struggle with a 5-step river crossing. It's not the length, it's the difficulty of the thinking required for each step.
That's the argument. Using just the number of moves as your complexity metric completely misses this crucial difference. It conflates execution length with problem-solving difficulty.
Okay, so putting this all together, this deep dive into Opus and Lawson's critique, it really reframes that initial accuracy collapse story, doesn't it?
It really does. If you look at the bigger picture, the original Shojay et al. Results, they are interesting, but maybe more as engineering insights. They show us, yeah, models can't output more tokens than their limits allow, sure. They show that automated evaluation can miss important nuances, like spotting impossible problems. Okay. And they show that just counting solution steps is a poor way to judge how hard a reasoning task actually is.
But not necessarily that the models have some fundamental reasoning deficit.
Exactly. Those conclusions about inherent reasoning limits don't seem well supported when you account for these evaluation issues raised by Opus and Lawson.
So the really provocative question that comes out of this deep dive seems to be, maybe the challenge isn't just whether these LRMs can reason effectively, but whether our tests are good enough to actually see that reasoning, or if we're just measuring how well they can, well, type under very specific, sometimes flawed conditions.
That's a fantastic way to put it, and it leads to a really important question for you listening to this. As these AI models get more and more capable, how do we get smarter about testing them? How do we design evaluations that truly probe their understanding and reasoning, getting past these surface-level output issues or poorly chosen metrics? That's the challenge going forward, I think. Designing tests as smart as the AIs we're trying to understand